So at this point, you should have been working on some of the activities for the existence part of the fundamental theorem of arithmetic. If you have not or don't feel like you have enough, I encourage you to go back and look at those. They'll help you understand this video a lot better. So we're going to be looking at the existence proof of the fundamental theorem of arithmetic. We're going to do a few things. First of all, we're going to review what the statement of the fundamental theorem of arithmetic is. We are going to actually prove the existence part of the theorem using strong induction. And then your next set of activities is going to have to do with the uniqueness part of the theorem. This video will set things up so that you understand the issues involved. So here's the statement of the theorem. Every integer that is at least 2 is prime or has a prime factorization. That's the existence part. It says a prime factorization exists for every every integer that is at least 2. And then the uniqueness part says the prime factorization is unique up to the order of the primes in the factorization are written. In other words, you can have a different prime factorization if you take the same prime factorization and just write the prime numbers in a different order, but that's the only way that you can make it different. So we're going to prove this by strong induction. So our base case is, well, we're saying every integer that is at least 2, so our base case is going to be n equals 2. So n equals 2 is prime, so we're done with the base case. That wasn't so bad. Now for the inductive step, what we're going to do is we're going to assume that k is greater than or equal to 2. We're going to assume for our induction hypothesis that all integers between 2 and k, and if k equals 2, that's just 2, right? All integers between 2 and k are prime or have prime factorizations. And we're going to show that k plus 1 is either prime or has a prime factorization. So here's our strategy for our inductive step. We have two possibilities. Either k plus 1 is already prime, in which case we're done because we just have to prove that it is prime or has a prime factorization. Or we look at the case that k plus 1 is not prime. In that case, we want k plus 1 to equal, k plus 1 should equal r times s, where r and s are between 2 and k. And then we'll use the prime factorizations of both r and s to find a prime factorization for k plus 1. Those were the strategies you hopefully used in the activities that you just worked on. But before we do that, we need a little theorem about integers that are not prime before we do that. I mean, because being able to factor k plus 1 into r times s is really important, but that's not part of the definition of not being prime. So we're going to talk about composite numbers, which is another way of talking about numbers that aren't prime, or at least most of the numbers that aren't prime, as you'll see. A natural number n is composite if it is both at least 2 and is not prime. Note again that 1 is not composite, since composite numbers have to be at least 2. The reason being that number 1 is not really part of the fundamental theorem of arithmetic, so we leave it out of the whole prime composite distinctions. And that means that 1 is neither prime nor composite. Poor 1. But it has a lot of other things going for it, so don't feel too bad. All right, so our supporting theorem is going to say that when n is composite, this is true if and only if you can factor n into two factors where each of those factors, r and s, are between 2 and n minus 1. Now, intuitively, this makes sense, but this doesn't follow directly from the theorem or from the definition. We actually have to prove this. All right, so here's the proof. So it's an if and only if, so we've got to prove the theorem in two directions. So first we're going to assume that n is composite, and we're going to show that we can factor it into two numbers, r times s, such that r and s are between 2 and n minus 1. So we know n is greater than or equal to 2. We know n is not prime. That means there is a divisor of n that is not n and not 1, because if that were not the case, then n would be prime. So we're going to just say r is one of those divisors that's not n and not 1. So we know it's not equal to 1. That means it has to be at least 2. And we know it's not equal to n, so it has to be at most n minus 1. So right now we're kind of halfway there, right? The r part of the factorization is between 2 and n minus 1. Now we know r divides evenly into n, and by the definition of divisibility, that means there's some integer s such that n is equal to r times s. So now we're almost there. We just have to prove that s is between 2 and n minus 1, and we've got the first direction of our theorem. So let's suppose for contradiction that we had s is equal to 1. Well, if that's the case, remember n is equal to r times s equals 1, so that's r times 1, and that means that n is equal to r. But we know that r is not equal to n. It can be at most n minus 1, so that's a contradiction. So we can't have s equals 1. Well, that means s has to be at least 2. Now suppose for contradiction that we had s equal to n. Well, again, we have n equals r times s. If s equals n, that's equal to r times n. By doing a little bit of algebra magic, that means that that can only happen if r is equal to 1. But again, we know r is not equal to 1, right? It is at least 2, so we can't have s equals n. But if we can't have s equals n, that means s has to be at most n minus 1. Putting that together, we get s is between 2 and n minus 1, and that gives us the first direction of our proof. For the other direction, we're going to assume that n is equal to r times s, with r and s both between 2 and n minus 1, and we're going to show that n is composite. Well, this isn't actually going to be very hard at all, because we know that r and s are both greater than or equal to 2, and if they're both greater than or equal to 2, when we multiply them together, that gives us a number n that is also greater than or equal to 2. So also, r divides evenly into n, but r is not equal to 1 and r is not equal to n. That implies that n is not prime, right? It has a factor that is not 1 and not n. So n is not prime, it is at least equal to 2, and then that tells us that n is composite. All right, that completes our proof. So now on to proving the existence part, at least, of the fundamental theorem of arithmetic. All right, so we're going to prove this by strong induction. And the way strong induction works is we have a base case, right? We're going to prove the theorem for n equals 2, but since 2 is prime, we're done. Now for the inductive step, we got to set up our assumptions and what we're trying to show. So we first have to assume that k is greater than or equal to 2, and for strong induction, we assume every integer between 2 and k satisfies the theorem. In other words, it's either prime or has a prime factorization. And we're going to show that k plus 1 is either prime or has a prime factorization. Now remember, the way we were setting up these cases are either k plus 1 is prime or it's not prime, right? Those are the only two possibilities. So for our first case, k plus 1 is prime. That one's easy. We just got to prove that k plus 1 is either prime or has a prime factorization. By assumption, it's already prime, so we are done, right? Again, this is a silly proof, but as we saw in the activities, it's an important place to start because it helps us do our cases. So we're done with that. Now the case 2 is the harder one. That is where k plus 1 is composite. Well, we already had a theorem that said that anytime we have a composite number, we can write it as the r times s, where both of those factors are between 2 and k. By our induction hypothesis, each of r and s is either prime or has a prime factorization. Remember, any number between 2 and k, by our assumption, has a prime factorization. Since r and s are between 2 and k, each of them has a prime factorization. So let's see, or it could be prime, right? So that gives us 4 possibilities. One possibility is both the numbers are prime. If that's the case, if I write k plus 1 equals r times s, r and s are both primes, that's the prime factorization of k plus 1. One of the other possibilities is r is prime, but s is a product of primes, has a prime factorization, q1 times q2 all the way to qm, where the qi are primes, right? But k plus 1 is equal to r times s. If we substitute the prime factorization in for s, we get r times q1, q2, all the way to qm. Now all those factors are prime numbers, so that's a prime factorization of k plus 1. Another possibility is r has a prime factorization, s is prime. That's going to work exactly the same way, except you're going to have the prime factorization times s, which gives you a prime factorization of k plus 1. And then finally, the most complicated one is when r has prime factorization, s has a prime factorization. So we're writing r equal p1 times p2 all the way up to pl, where all the p's are primes. S is equal to q1 times q2 all the way up to qm, where all the q's are primes. Well, guess what? K plus 1 is equal to r times s, and that's just multiplying the two prime factorizations together. We get a prime factorization of k plus 1. So for all the possibilities for r and s being either prime or having a prime factorization, that gives k plus 1 a prime factorization as well, and that completes the inductive step, which completes the proof of the theorem. So now that just leaves the uniqueness part of the proof. Now I'm not going to do that proof in this video. That's way too much because this video is already pretty much too long. But I do want to help set you up for the activities for the uniqueness part to show you the issues involved. We're going to do a proof by contradiction, which is kind of how our uniqueness works, right? We've done uniqueness proofs before with the division algorithm, and this is going to be very similar. So what we're going to do is we're going to assume that n has at least two prime factorizations and then prove that it really doesn't. Find some kind of contradiction. So the first thing we got to ask ourselves is, okay, well, if we're assuming it has at least two prime factorizations, what are all the ways that prime factorizations can be different? Well, the prime factorizations can have different prime numbers in them. Right? Or at least one of the prime numbers is different, is in one but not the other. Or one of the they could have the same prime numbers in them, but one of the factorizations has more factors in it than the other, right? So we're going to assume that the n could be equal to p1 times p2 all the way to pm. That's one prime factorization. The other prime factorization is going to be q1 times q2 times all the way to qt. And so you can see we do two things, right? Where each of the p's and q's is prime. We're doing two things here, right? First of all, notice that the number of primes in the first prime factorization is m, and the second is t. So we're leaving open the possibility that we could have a different number of primes in each one, right? So if we were to show that m is equal to t, that tells us that both prime factorizations have the same number of primes. And then we're also using different variables for the primes in the first prime factorizations and the first and the second. So the second thing we'd have to prove is that if we rearrange the numbers, we can make it so that the prime numbers match up. So the pi equals qi for each I if we rearrange them in a certain way. All right, so that should get you set up for the proof of the fundamental theorem of arithmetic, the uniqueness part. That's basically what the file name is on the activities that you'll be working on next.